So we are dealing with compact operators, okay, and we have proved the following. We have given some characterization of some properties of compact operators. Then we want to prove the spectral theorem for compact operators, and towards that we proved the following. We proved this following proposition. It's clear, no? So proposition is if T is a compact operator and T is normal, T is normal, then there exists an eigenvalue lambda such that there exists an eigenvector x naught with, of course, you can take it to be norm x naught equal to 1, such that T x naught equal to lambda x naught. That's what eigenvalue means, eigenvector means, and mod lambda equal to norm T. Okay. So we proved this, except we proved the following. We proved provided we prove the following proposition. We prove the following lemma. So the lemma is the following. So we have proved this proposition using this following lemma, and the lemma is if T is normal, this is for any operator, then norm T equals supremum of norm x less than or equal to 1 mod of Txx. So we want to prove this lemma. This lemma in the last year course, the same course, we proved this lemma using what is called spectral radius formula, and spectral radius formula for then the spectral radius is actually equal to norm T. But then we used approximate eigenvalues to prove this. But since we haven't talked about spectral radius and all those things, we follow a different proof. Okay, so I give you a completely different proof now. Okay, so to prove that I define the following. So this is definition. For T in B of H, define, let's say, triple norm T equal to supremum of x and x in norm x less. I mean, this is in B of H, so norm x less than or equal to 1, and this value. Okay, then the following thing holds. Then clearly this is a semi-norm. I mean, this is you can see that this is a semi-norm. It satisfies. You can take an alpha out. I mean, if you have an alpha here, then you can take it out. Take it out as mod alpha, and this satisfies triangle inequality, except what is except the I mean, if triple norm T equals 0 should imply T equal to 0, except that everything is clear. So then T is a triple norm. This is clear. Okay. So I think we defined what is called a semi-norm. Okay, this satisfies, except that the positivity property, the faithfulness property of norm, everything else is true. Okay, this is a semi-norm, and we also have the following. We also have that for any Tx. So this is defined as a supremum over the unit ball. So this is true for all x. This is triple norm T times norm x square. This is as direct, right? You just have to, I mean, take y is equal to x by norm x. Okay, then tyy. I mean, this is less than or equal to 1. The norm of y is less than or equal to 1. So tyy is less than or equal to norm t. And from that it follows. Okay, from that it follows. So these are the two properties, that it's a semi-norm and it also satisfies this. We want to prove actually it is a norm. And then we want to prove that for normal operator, this norm coincides with the original norm. This is not true for every operator. For normal operator, this triple norm, whatever we have defined, is actually equal to the original norm. That's what we want to prove. Okay. So the way I keep, it's not comfortable for me. Okay. So we prove the following proposition. Okay. So what did we prove? We prove that T is in B of H. Then this triple norm T is a norm and it is equivalent to the original norm T. So the operator norm. We have defined an operator norm and this is equivalent to that. So towards that we prove the following. We prove that half of norm T is less than or equal to triple norm T is less than or equal to norm T. Anyway, this is clear, I believe. Okay. See, this Txx is less than or equal to norm T for all x, norm x less than or equal to 1. So this implies triple norm T is less than or equal to norm T. So this is clear. One way is clear. Okay. So we only have to, so this is, so triple norm T is less than or equal to norm T. So is there anything hiding here? Is that fine? Actually, in the screen, I am not able to see what is written in the right corner. So if you can see, it's fine. If you don't see, you tell me. I don't know how to get it right. If I move here, maybe it will work. I'm not able to move the other one. Okay, it's okay. I hope it's fine. Okay. In my screen, something I have written in the right corner is not visible to me. Hope it's visible to you. Okay. If it is not visible, you tell me. Okay. So we want to prove this proposition. Okay. Okay. So, okay. So this is one thing. And further, we want to prove that further, if T is normal, this is true for all T, any T. Okay. If T is normal, then norm T is equal to this. So this is what we want. Okay. Okay. So this inequality, whatever we have written here, this triple norm T is greater than or equal to half times norm T will imply that it's a norm. Okay. Is a norm. We want to prove this lemma, okay, which says that norm T is equal to this for normal operator. And we are defining this for every operator and prove that that gives a norm. And that norm is equivalent to, this is what equivalence means, okay? This whatever I have written. I mean, there exists constant, which makes it constant times one norm is greater than the other norm. Okay, that's what equivalence means. We have talked this earlier. Okay. This is equivalent to the original norm, and also it follows that norm. I mean, for normal operator, norm T is equal to triple norm T. Okay. So proof. Okay, so we want to prove the following. We want to prove this this inequality, whatever I have written. So to prove this, let me compute the following. So we want to consider txx, now inner product txx. So I compute this tx plus y, x plus y, this inner product. Okay. Then I should take minus t x minus y, x minus y. So this is equal to, if you take the sum, txx will come and tyy will come, minus will become plus, and then other things will cancel. So this is equal to, I think, 2 times this, 2 times tx y. I mean, since there is a minus, only the cross terms will be there, okay? Plus 2 tyx. Is it fine? If that is minus, this is minus. It's just a linear property of the inner product, and just if you look at it, manipulation will give you this, okay? So this is okay. Now the LHS, if you take the LHS, norm of, mod of LHS, which is just a complex number, so mod of LHS, so that is less than or equal to, so I can take, I can take the plus of that, and then this is less than or equal to norm T, triple norm T. So I'm using this inequality, okay? That, where is it now? I've used this, okay? I want to use this. Okay. This txx is less than or equal to norm triple norm T times norm x square, okay? So I want to use that. That will imply that this, whatever the LHS is, norm triple norm T times that whatever x plus y norm square plus x minus y norm square, right? Now that is equal to triple norm T times this, this is equal to norm x square plus norm y square. And if norm x, norm y less than or equal to 1, then this implies mod of LHS is less than or equal to 2 times this. Okay. And in fact, we want to get that. Okay. Norm T is less than or equal to 2 times triple norm T. That's what we want to get. So towards that, I'm proving this. Okay. This is fine. Okay. So this is fine. So right hand side is also less than, modulus of the right hand side is also less than that. So for any xy, see here there is no x or y. Okay, the LHS is the left hand side is less than or equal to 2 times triple norm x for all x and y whose norm is less than or equal to 1. Okay, so now this is true for the left hand side, right hand side also. So for the right hand side, I want to take any x and y. So in particular, I take the following. I take y equal to, I want to deal with this triple norm or double norm, right? So I am using this x by norm. I don't want to take this. I want to take this tx. I want to take something of norm equal to 1. Okay. I mean, of course, we always assume x not equal to 1, not equal to 0. Okay, x not equal to 0. And for any x, for any x, this is true. Okay.
4 times triple norm of T.
Say it again.
LHS less or equal to 4 times triple norm of T.
2 times, no? This is 1 norm, x is of norm 1. Oh, this is 4, is it? 2 plus 1 plus 1, yeah, this is 4, right? Yeah. That's right. So it should be 4. 4 means then I may get a different number. Let me see. Is it 4 or something? It is, well, it's 2. Yeah, it is 4, correct. Okay, let's see what we get. Okay, so it's right. Okay, it's 4. Good, thanks. Okay, now I take the following. Okay, maybe we will get a 2 here, so it will get cancelled. Okay. Okay, now y equal to this. So then the right hand side becomes the following. The right hand side is here. Okay, so I'm just substituting this particular y here. So the right hand side is equal to, if we substitute this, then the right hand side becomes, then I mean I take the mod right hand side. Okay, so mod right hand side, which is less than or equal to, take this 4 times norm triple norm t, greater than or equal to, I mean the mod right hand side also. But then mod is mod right hand side, which is equal to mod of so there is a 2 there anyway, so that's good. That is how the 2 will go. Okay, so 2 is there 2 times. So tx, right? tx and divided by that. So divided by norm tx. Okay, plus then ty x is there. So which is t square x, right? T square xx divided by norm dx, right? Okay, so these things imply that norm tx, I mean this is norm tx square, so I get norm tx times this tx inverse of t square xx. Okay. Mod of this is less than or equal to triple naught. Okay, 2 times triple naught. Okay, now I got the 2. So in particular, the mod is less than or equal to this. In particular, the real part will be less than or equal to that. Okay. So then the real part is just the this implies norm tx plus tx inverse. Real part of this is less than or equal to 2 times this. Okay. But then if you see, this is here, you have a x here. This is true for all x. Okay. This is true. Sorry, this is true for all x. It's not just less than or equal to that. This is true for all x, because we have taken, yeah. This cannot be true for all x. This is true for norm x less than or equal to 1. I mean, we have used some the tx by this, but still it is true for only norm x less than or equal to 1, because we are using the y also. We have taken y to be this, but then x should be less than or equal to 1. Norm x should have norm less than or equal to 1. Okay. Okay. So this is true for all x, norm x less than or equal to 1. So if this is true for all x, then you can take some alpha times x, something with mod alpha equal to 1. Okay. For example, if then you can get rid of the real part and get the modulus there. I mean, this alpha, you can take any alpha. If you take alpha in this norm, that alpha will go away. And here also the alpha will go away. And then the inner product, you will get the alpha. You will, so that alpha you will get multiply by mod alpha, right? No, not mod alpha. If you, yeah, you want to talk about the real part of that. If you take alpha here, that will become, if you have some z, I mean, if z is equal to some r times e power I theta, okay, you have t square xx, you know? So, no, not by taking t, by taking alpha. So, sorry, this is not by taking t. I think you have to take the, this is anyway true for all t, right? This is true for all t. So you can take mod alpha, I mean, you can replace t by, I'm sorry, you can replace t by alpha t. So then it will work. I mean, if you replace x by alpha times x, you will get only mod alpha, which is equal to 1. You will not get anything. So you have to replace t by alpha t. Okay. Then you will get alpha square here. You can take the alpha square out. That is a complex number. And see, this is just real part of something. So the real part of something you can multiply by a complex number to get to its modulus, right? If we have some z, okay, then you can multiply by alpha to get, so that the real part of, so that the real part of this will be mod z. Is this okay with everyone? For example, if z is equal to r e power I theta, okay, the real part is going to be r cos theta or something. So if you multiply by e power minus I theta, okay, then you get r. Real part of z will become r, right?
And mod alpha is 1.
What is it?
Mod alpha is 1 here.
Mod alpha is 1, right? That is why you can take it about e power minus theta. I'm just saying that you can multiply by a mod alpha and make this, you can replace t by alpha t. So you will get an alpha out. So by multiplying a complex number, here you have the freedom of multiplying. So by multiplying by using this alpha, you can get mod of that. See, if you have, that's what I'm saying. If you have z is equal to r e power I theta, okay, then you can take an alpha z such that real part of this alpha z is equal to r. You just have to multiply by e power minus I theta. You can take any alpha, right? So I'm just saying by replacing replacing t by alpha t, we get the following. We get norm tx plus whatever the tx inverse times mod of that, mod of t square xx, okay, is less than or equal to 2 times norm t. Okay, this is fine for all norm x less than or equal to 1. Okay. Okay. So this implies, of course, so this is a positive. This is whatever we have here positive. The second term is positive. So this implies norm tx is less than or equal to 2 times norm t for all norm x less than or equal to 1. So this implies norm t is less than or equal to 2 times norm t. Okay. So we have proved one of them. We have proved this. Okay. Proved this inequality. Okay. So next we want, so we call this a star or something. This. Okay. Now we want to consider normal operator. So for that, we take everything to the other side. Okay. Star implies, so this tx square plus mod of t square xx. Okay. We want to take everything to the other side. So minus this plus 2 times triple norm t, okay, is greater than or equal to 0, right? And triple norm t, and you will have your norm tx here, right? No, you will not have norm. No, you don't have to. That is what that has been taken there. But then you will have here, right? Is okay. Minus tx square 2 times this minus this equal to 0, right? This is fine. I have just taken it to the other side. Okay, that's all. This is greater than or equal to 0. Okay. Now this I can write it as these two. These are square, right? So minus of norm tx plus triple norm t whole square. Right. So plus I have taken something there. So norm square minus t square xx is greater than mod of this is greater than or equal to 0. Anyway, this is negative. This is less than or equal to 0. So this implies that triple norm t square is greater than or equal to norm t square xx. Right? So this implies triple norm of t square is less than or equal to triple norm of t square. Is it clear? I mean, I have this, I mean, I derived the star, okay, just by writing the inner product. Then I have taken the whole thing on the other side and I have removed a negative term. Okay. So then I got this inequality. So this just says that, I mean, this is true for any norm also. If you know, so you should know that if you have any, ST, this is true, no? Norm of ST is less than or equal to, this is for any operator norm, norm S test norm T. So in particular, if you have norm T square, that is less than or equal to norm T times norm square. So I'm just saying the same thing is satisfied by this triple norm also. Okay. Okay. So that is what I have got. Now using this, I want to derive that the triple norm is same for normal operator. So now if T is normal, so this thing I think Shruti also discussed. If T is normal, the first thing is, I mean, this is true for any operator. Norm of T star T is equal to norm T square. Okay, for all T. This is not for normal operator. For all T. Okay. So you okay. This is true for all T. Now we want to talk about. Okay, let me write the whole thing and then let us see what we get. Norm 2 power n. Okay. So I ask, this is what is called C star identity. Okay. It is just the name. And Shruti proved this. Norm T star T equal to this. Okay. Now if T is normal. See, this is the problem with writing with the bigger board. You can't see much in the screen. Okay. Anyway, I'm just going to use this inequality only. Now T is normal, then norm T power 2 power n. Okay, that is equal to norm T star T power, I mean, whole power half. This is okay. Okay. Now T star T is self-adjoint. Okay, for any self-adjoint operator, if you use this this C star identity, I mean, norm S square equal to S power half star S power half. Okay. I mean, S star S we want to write. So this power half star S star, right? So that is equal to, no, I mean, no, if T is self-adjoint, then T star equal to T. So if we just use it, then that is just for self-adjoint T, norm S square equal to norm S. Okay. So because of that, this implies norm, this is equal to whatever we have here. Is equal to norm. So you can take this I mean, once you can take once you can take one, I mean, a square inside, then you can take any power of square. Okay. So 2 power n, you can take it inside. That is equal to T star T power 2 power n. This is okay. Because it's self-adjoint. Okay. The whole power half I have here. Now I'm using the fact that it is normal. So this is just going to be T star T repeated 2 power n times. but T star and T commutes because it's normal. So because of that, this is going to be T star power 2 power n, T power 2 power n, which is, of course, you can take the power inside. So that is equal to, you can take, I mean, that just means that you can take T power 2n, T star power, T power 2n star, T power 2n, 2n, not 2n, 2 power n, over half. And that is equal to, we have started with outside, so we get it inside. Now this is equal to, we can take the, remove the half, and you get that T power 2 power n. Okay. What I have proved is, if T is normal, this is not true for every operator. If T is normal, then T power 2 power n. I think Shruti proved this. I don't know. I'm just proving it again. Okay. I think she started proving, then I interrupted, saying that we haven't proved spectral radius formula. I mean, this is part of proving that spectral radius is equal to norm T, whatever it means. Okay. I've just proved this for T and for normal operator. Okay. Okay. So now I prove the following. So now norm T power 2 power n is equal to norm T 2 power n, which is less than or equal to 2 power triple norm T power 2 power n. So now I use this inequality. Okay, whatever I have in the rectangle, I use this inequality. I can take the square outside. So that is less than or equal to 2 times triple norm T. I mean, you can take a square out, you can take a 2 power n out. Okay, 2 power n. Okay, this implies norm T by, we assume T is not equal to 0. Okay, norm T whole power 2 power n is less than or equal to 2. So for all n, okay, so this shouldn't be that should be less than or equal to 1. Otherwise, it's not possible. If it is greater than or equal to 1, it will be, or it should be equal to 1. Okay, this implies this is equal to less than or equal to norm triple norm. Okay, we have already proved the other. This is right. So we have already proved the other way. So this implies norm T equal to norm triple norm T if T is not. Okay. So this is the direct operator theoretic proof. The other proof is what is C-star algebra proof. So if you want to prove that whatever the lemma, what we have proved, you have to compute the spectral radius formula, and the spectral radius formula will imply that norm T is equal to spectral radius for normal operator. Then using approximate eigenvalues, you can prove it. Okay, but here we are proving, giving it. I mean, I have given a direct proof. Okay, this is equal to this, just using the manipulation of operators. So I think it's clear. If you have any specific doubt, you can ask me. I will recall the whole proof. Okay. We want to prove this inequality, that norm T equal to this for normal operator. Towards that, we define the triple norm T and show this inequality and prove that this triple norm T and they are same. So I am just taking something and I'm expanding this like this. Then I take the LHS, which is less than or equal to some triple norm T. Then I substitute some particular y. Then I get an inequality. Then using that inequality, I just remove a positive term and then show that show the required inequality, that triple norm T is greater than half times norm T. So then I do something. I mean, use the same inequality and prove that the square can be taken out by inequality. I mean, by the triple norm of T square is less than or equal to triple norm T of T square. Then this is just a routine thing for normal operators. Okay, this is just a routine thing for normal operator where you can take T square, I mean, the square outside a norm. I mean, in a sense, you can take 2 power n outside. Okay? So I have just used this. So that is the idea. So go and look at it. If you have any problem, you can tell me. I have written it clearly. Okay, everything is written clearly. Okay. So we have proved that, and we have proved the following proposition. We have proved the following proposition now. The proposition is, if T is compact normal, then there exists an eigenvector. I mean, it first says there is an eigenvector And then that eigenvector, then I mean, this is just I mean, actually, to prove the spectral theorem, we only need one eigenvector. We just need a existence of eigenvector for a normal operator. Okay, we don't really. If we have one, then using Zorn's lemma, we will get many of them. Okay, we will get all of them. Okay, as a theorem, not we can get it in reality, but as a theorem, we can get all of them. So then there is an eigenvalue whose mod of the eigenvalue is equal to norm t. Okay, so now we prove the spectral theorem. So what is spectral theorem? T is k of h. T is a compact operator and T is normal. Then there exists, I mean, we have already proved if it is a diagonal operator, okay, then, I mean, if there exists eigenvalues and eigenvectors, then the lambda n has to go to 0. Okay, here we are proving the other way. Then there exists eigenvectors. No, there exists an orthonormal basis of eigenvectors. That's what I want. Then there exists an orthonormal basis En of eigenvectors. Okay, and eigenvalues lambda n with lambda n going to 0. Okay. That's all. I mean, we have T En equal to lambda n En. Okay, and En is Ynb. These are the conditions, and lambda n goes to 0. Okay, this is for a compact operator. So these are the three things we have to prove. We have already, I mean, we only have to prove the existence of orthonormal basis as eigenvectors, and then lambda n going to 0 is already proved. Okay, for any diagonal operator is a compact operator, if and only if lambda n goes to 0, we have already proved in the last class. So we only have to prove the existence of eigenvalues. For that, we use Zorn's lemma. Okay, Zorn's lemma is used already several times, so we are using it again. Okay, first we know that there exists a lambda. I mean, to show Zorn's lemma, we have a collection of partial ordered set, and that should be non-empty. So because of that, okay, there exists a eigenvector. Maybe x with mod lambda with eigenvalue lambda with mod lambda equal to norm t. Okay, now we take the collection of orthonormal set with I mean, which are eigenvalues, which are eigenvectors. Okay. Orthonormal set with forming an eigenvector for the grid. Containing eigenvectors. Okay. Okay. Then usual inclusion. Okay, with I mean, this is with inclusion. As partial order. Okay, it's a partially ordered set. So you verify, I mean, it's clear that the axioms, I mean, the conditions of Zorn's lemma is satisfied. I mean, every total ordered set will have an upper bound, and it forms it. I mean, every chain has an upper bound. So this implies there exists a maximal element. So let n equal to 1 to infinity be a maximal element. Okay. Be a maximal element. Okay. And we want to prove that this is actually an orthonormal basis. This is an orthonormal set. Okay, orthonormal set, and we want to prove that it's an orthonormal basis. Okay, so if it is not an orthonormal basis, suppose, then we have to prove that it's not actually a maximal element. That's what we want to do. Suppose E is not an orthonormal basis, not a ONB, okay, not an orthonormal basis. Okay, then let P from H to span closure of E, okay, be the projection, orthogonal projection. Okay. Okay. Then we compute this TPX for X in H. We compute this TPX. What is TPX? That is T acting on PX, right? So which is equal to T acting on, what is PX? Which, I mean, any X can be written as XEN summation, right? For orthonormal basis. But PX is just an element in this span of this, right? So PX, any PX will look like this. Summation n equal to 1 to infinity XEN, right? This En is orthonormal basis for pH, right? Okay, the range of P, it is an orthonormal basis for that. So any Px can be written like this. Okay, is okay. Okay. Now T is continuous. You can take it inside the infinite summation, and it's linear. You can take all these things. So T, XEN, En, TEN, right? But then TEN is lambda n En, and then that two things I completely forgot. Okay. I mean, this is, you know, from linear algebra, I think. Okay. I will write this lemma. I will prove it after this. Okay. I mean, this you must be knowing. If lambda is an eigenvalue, for T is normal. Okay. Then lambda bar is an eigenvalue for T star with same eigenvector. Okay. This you know for matrix, I believe. So this the same thing is true here, but it's T should be normal. And also, if I don't know why this comes. I don't touch anything. So if further, if lambda, mu are two eigenvalues with eigenvectors x comma y respectively, okay, and lambda is not equal to mu, okay, then x is orthogonal to y. I am sure you know this also for matrices, but this is true for this is true in general also. Okay, so that is what I'm going to use here. So now, so once we have this lemma, then whatever we have here, TPX, the TPX, which is equal to that summation, whatever summation n equal to 1 to infinity XEN TEN. TEN is just lambda n En, but that lambda n En, I can take it inside. So that is equal to summation n equal to 1 to infinity X lambda n bar En. I mean, this is the second and I mean, this inner product, it will go as a bar, right? En. So this is equal to n equal to 1 to infinity x t en en. Okay, sorry, t star en, because that's an eigenvalue for t star with the same eigenvector. Okay, that is equal to n to 1 to infinity tx en en. But then here the tx is expanded in terms of en, which is an orthonormal basis for ph. Okay, so this is equal to ptx. So I am writing all these things to prove just this. Okay, tpx equal to ptx. So these things imply that if you have two normal operators, a projection is a normal operator, it's self-adjoint, so it's normal in particular, and T is a normal operator. If you have two normal operator, then if you have a normal operator S and a normal operator T, then ST is normal if and only if S and T commutes. Okay, so here T and P commutes. This implies TP is normal. Okay, which of course implies 1 minus PT is normal. Okay, so 1 minus PT is something. So in particular, I mean, see if some, you know that these things we should have verified when we started the Hilbert space theory, but we might be knowing in terms, see, any operator, if you have a projection P from H to H is a projection. Okay, then any operator T can be written as T1, T2, T3, T4. Okay, and if T commutes with PT, then this T2 and T3 are 0. Then T is equal to T1, T4. Okay, this is true for any. I mean, this is like matrix. You just multiply as a matrix. Okay, you can write it as a matrix like this. That is H is equal to PH plus 1 minus PH, right? Direct sum. So with respect to this direct sum, I am writing this as a matrix like this. It is a matrix containing operators, 2 cross 2 matrix of operators. And you can multiply like you multiply matrices. Then you get this. Okay, PT equal to TP. Okay. So that is the condition. So if so our T is equal to, this basically says that T is equal to PT direct sum 1 minus PT. Okay, that's what this says as operators. It acts separately on the direct sum of these two Hilbert spaces. Okay. Now we know that PT 1 minus PT is a normal operator. So if 1 minus PT equals 0, then any x in 1 minus PH is an eigenvector. For T, right? That's clear. Tx is, I mean, okay. You can just, I mean, 1 minus PT is just nothing but T on this 1 minus P times H. So it's clear. If 1 minus PT is not equal to 0, and since it is normal, there exists an eigenvector x in 1 minus PH with norm lambda equal to 1 minus PT. We have proved it already. In both the cases, E is not maximal, okay, which is a contradiction. Okay, so these things imply that E is orthonormal basis for H, which implies that there exists a orthonormal basis of eigenvectors for this. Okay, I have written elaborately, but it's very simple. Okay, if you have any doubt, you ask me. I have to prove only this lemma. Okay, any question? I mean, you can ask about the idea. I can summarize the idea. Or if you have any specific doubt, you ask me. No problem.
First,
Say it.
first line, can you explain once the
Which is the
TPX
first line?
equals-
Very first line. Here. Here.
Where, this line TPX equals to this sum.
No, if you have, what is PX? So let me explain here. What is, so I have a projection from H, which is taking values in pH, right? I mean, which is its range is pH, right? So pH is a subspace. Okay.
Yeah.
This En, whatever the Dn, we have defined that P to be the subspace spanned by this En. So this En is an orthonormal basis for pH. Okay. Any vector in pH, any vector in pH. If you have any vector in a Hilbert space, you can expand it through an orthonormal basis. In particular, any vector in pH, any vector, okay, any vector in pH can be expanded as in terms of this, using this dot En summation. Any vector you can write. If you have any Hilbert space, then this X is equal to Xen, where this is a series which converges, okay, in the Hilbert space now, in the topology. This is an infinite series. You have to make sense of convergence. It converges in the infinite series topology. So if you have any orthonormal basis, then this is how you expand. For this pH, this En is an orthonormal basis. I mean, it is an orthonormal set in H, but we have defined P so that it is an orthonormal basis. That is how we have defined P. No, P is a projection here. P is a projection from H to span.
This line is okay, I can get this, but why the lambda n bar En that time comes, that I can't get it.
Let me come to that. Okay, so one second, let me erase this. This is an so what is your question? Here, no? Here, this is clear, right? So the first line is clear. This line is clear. I put a tick. Okay, that is clear.
No, why lambda n bar is coming? That's my problem.
Why lambda n bar is coming? That is because Hilbert space, if you have any alpha, if you have a number alpha in a inner product space, if you have alpha times inner product xy is equal to x times alpha bar y. What is the problem? We get a lambda here because En is an eigenvalue for that, right?
Okay. I got it.
En T equal to lambda n En that we are assuming, right? It is because of that I get a lambda. So I have just, I mean, I didn't want to two lines. So I put a T. I said orally Ten equal to lambda n En. Then that lambda n I take it as a lambda n.
Yeah. Then it's okay.
Yeah. So that's why. And I have to prove this, whatever that lemma. Okay, I still have to prove that. So any other doubt? Let me show you. TPX equal to, I mean, I have just used Zorn's lemma. We proved a proposition which ensures us there is one eigenvalue with, of course, an eigenvector. Then we use Zorn's lemma to get a maximal subset of orthonormal set. Then we want to prove that that is equal, that is an orthonormal basis. That proves that that's what we want to prove. So if not, then we take the projection. I mean, we do this computation and prove that TP is equal to PT, which will imply that 1 minus PT is normal. So in the orthogonal complement of the span of those E's, the orthonormal set we have got, we have an eigenvalue, which will imply that we have an eigenvector, which will imply that that set is not maximal. Okay, so that is what we have proved. So anybody else? Okay, no doubt. So let me prove this lemma. What is it lemma? I will write it again. Lemma. T is normal. This is true for any normal operator. Need not be compact. Okay. Then if T x equal to lambda x, then T star x equal to lambda bar x. Okay. Further, if Tx equal to, I mean, that's what I have orally said. Okay, here I'm writing using the definition. Tx equal to lambda x and Ty equal to mu y. Okay, and lambda not equal to mu. Eigenvectors corresponding to different eigenvalues are orthogonal. Okay, that's what we are saying. Then x is orthogonal to y. Maybe I will write it using the definition. Then the inner product of x and y equals 0. Okay, that's what you have to prove. I think Shruti proved the following for normal operator. Norm Tx is equal to norm T star x. She proved it, no? Go and look at it. I mean, she proved it. This is certainly needed to prove the C star identity. Okay, so she proved it. So in particular, T minus lambda x is equal to T star minus lambda bar x. Okay, so if this is equal to 0, if this is equal to 0, then that is also equal to 0. So that's what that means. If lambda is an eigenvalue, lambda bar is an eigenvalue for T star. Okay, it's fine. Anyway, this is the same idea in matrices also. There is no difference. Okay, there is nothing about infinite dimensional Hilbert spaces. This is true for matrices also. On the other hand, we want to prove that if Tx equal to lambda x and Ty equal to mu y, lambda not equal to mu. Okay, so we can assume one of them is not equal to 0, that lambda is not equal to 0. Okay, then xy is equal to, you can put a lambda x here, 1 by lambda here, lambda xy. So which is equal to, which is the definition of Tx y, which is equal to 1 by lambda x T star y. By earlier thing, this is equal to 1 by lambda x mu bar y. You can put a mu bar y, and which is equal to, you can take it as mu by lambda into xy. Okay. So lambda is not equal to mu. So this should be always true. So this implies xy. Anyway, this is true about matrices also. The same thing. There is nothing about infinite dimension. Okay, so we have proved this. Fine. So that's all about compact operators. Compact operators. This is a spectral theorem for compact operators. Again, if you have questions, you can ask me now. If not, let us go to a new topic. Since I have 15 minutes, I will do that. Okay. I want to define. So now we have talked about compact operators. Now we want to talk about some particular class of compact operators called trace class operators and Hilbert-Smith operators. Okay. First, we will consider trace class operators. So to define trace class operator, I need to define what is called a trace. So trace is already defined in matrices. T is in M and C. Okay. Then, you know, trace of T is nothing but summation TII, the ith entry, which is also same as summation T EJ EI. I mean, this is the ijth entry, sorry, EI. Just the sum of the diagonal terms. Okay. Sum of the diagonal terms, that is what is called a trace. This trace from M and C to C is a linear functional. Okay. And it satisfies trace of xy, I mean for matrices, so maybe I should use capital letters, xy equal to trace of yx. Okay. So this is what is called tracial property. Okay. And on MMC, this functional is unique. I mean, this is the only functional which satisfies this equation. Okay. and the trace of 1 is n or something with other condition. Trace is unique, functional, call it star, satisfying star, and trace of the identity is n. Or you can normalize it and trace of 1 is 1 or something. We can put a 1 by n. You can define it. That is usually called small trace. This is what is called big trace. If you put a 1 by n, that is called small trace. Okay. So up to this constant multiple, the trace is unique. This is for finite dimension. So we want to extend this property for finite dimension. Incidentally, this trace, I think, is invented by physicists. I don't know that. I don't remember. I know the name, but I don't remember. See, there is this Dirac was trying to do something, and he couldn't define this trace on this infinite dimensional Hilbert space, and he was getting into contradiction. He spent several years struggling with that. Then this guy came up and found that there are some. I mean, you may not be able to define trace on whole of B of H when it is infinite dimensional, but you can define it on some particular class of operators. Then work with that, and the whole thing works like that. So which Dirac was not able to find it for a long time. So that is when someone young and someone who goes and works on it, you will get new ideas. This I heard it from physicists, so I'm not sure about the story. Okay. So that is how it started. Of course, anything in physics will, when we have a theory in mathematics on its own. So this is about trace class operator. So we want to define what is called a trace. Okay. So this is definition. Let T is in B of H. Okay. Then define, and T is positive. Okay. Then define trace of T equal to summation T En En. I have to fix the orthonormal basis. Okay. For H. Okay. Then define trace of T equal to summation T En En. Since all the T En, we have talked about positivity, no? So for positive operator is defined as Txx greater than 0. That is the definition of positive operators. Okay. So Shruti did that. So Ten is all greater than or equal to 0. This is a sum of positive numbers. So it can be, this trace is a value something in 0 to infinity. It may take the value infinity also. Okay. So this is well defined. If you include the value infinity, this is well defined for positive operators. The thing is, this depends on the orthonormal basis. We first want to prove it does not depend on the orthonormal basis. So that is the first thing we want to prove. So trace we are defining for positive operators, any positive operators, where this value can take infinite value also. Okay. And it depends on the orthonormal basis. First, we want to prove that it does not depend on orthonormal basis. So we use the following number. For T in B of H need not be positive. We can define it for any positive operator. So I hope you know that if T is positive, then T star T is positive. Okay. Positive operator. If you want. Okay. Okay. So they are positive operators. Okay. This is the definition of positive operator. I mean, this is just the explanation. Okay. If you have a T in B of H, then we can define trace of T star T. Okay. Similarly, we can define the trace of T star. So both are equal. Okay. Still, the orthonormal, I mean, the trace is depending upon orthonormal basis, which I am not writing. I mean, the next step, we will prove that it does not depend on the orthonormal basis. Okay. So this I want to prove. It's just a manipulation. So I want to calculate trace of T star T. Okay. So I have to write many things. Summation T star T, En, En. Okay. Which is equal to, I can take this is equal to, I can take the T star outside as Ten. Okay, summation Ten T. Okay. Which is equal to summation N equal to 1 to infinity. So Ten, I can expand this Ten, okay, in terms of orthogonal basis En, right? Okay, I can extend, I mean, Ten is an element in the Hilbert space. I can expand any element in the Hilbert space through an orthogonal basis. So since it's different terms, I'm using the different index En. Okay, so this is equal to summation. I can take the summation outside because inner product is continuous. Okay, En, En. Okay, so then that will come out. So Em T En. Okay, then we have to get into the star. Now this is, I mean, we know that these are all positive things. I mean, this term is just the bar of that. Okay, this is in the form of z bar. This is greater than or equal to 0. Okay, so this is positive terms. When you sum positive terms, you can interchange the summation. I mean, if it may be infinity, but it will still be infinity. You can't do that otherwise. So you can change the summation because they are all positive terms. Okay, interchanging the summation. I mean, in measure theory, you know the Fubini's theorem. This is just the, not Fubini's theorem. This is just the Tonelli's theorem. One theorem for positive function. If you take the counting measure, and then I'm just using that. Okay. Okay, I have interchanged the summation. So this becomes Ten, the same thing, Am, Em, Ten. Okay. Now I expand it in terms of N now. Keep it here. So where will I do that? Let me change this. Okay, I have taken the T to the other side. Now I can, here I can take the summation in the second summation. Okay, this is equal to En, T star En, summation N equal to, I will take it inside. I take it inside. T star En, En, okay, En, T star En, and I have the summation N equal to 1 to infinity. Okay. Summation M equal to 1 to infinity. Now we take the summation inside. T star En, En, En. This is just the expansion in terms of the orthogonal basis En. So this is just equal to just T star En. T star En. Okay. T star En, which is equal to trace of T star. We started with trace of T star T, and we ended up with trace of T star. Okay. It's just a, I mean, you can try anytime. Okay. Just take the summation and interchange the summation and you get it. And since I have been teaching, I have done it several times. Okay, I've gone through this calculation. I don't know, some 10, 20 times in the class. Okay. Last year also I've done this. Okay. So from this, I prove the following corollary. How much time I have? I have 2 minutes. Corollary. For T in B of H, T in B of H, yeah, T greater than or equal to 0, See, if we have any operator greater than 0, if t is greater than or equal to 0, then st s star is also greater than 0. Okay, because st s star x equal to yes. If you have a positive operator t, then you can write it as t power of s star xx. Okay. Now that is equal to, you can take it to the other side. S star t power half s star x. You can take the other way, t star t power half x. Okay. Now that is equal to norm of t power half sx square. So this is greater than or equal to 0. So because of that, if t is greater than or equal to 0, then st s star is greater than or equal to 0 for all s in B of h. Okay. I mean, since we have defined trace only for positive operators, I'm verifying all these things. So now if t is in B of h and t is greater than or equal to 0, and u is a unitary, this is just a verification for you. U in B of h is unitary. Okay. Then trace of ut u star. T is positive, so ut u star is also positive. So the trace makes sense here. This is equal to trace of t. Okay. Okay. So this is true for all t. All t greater than 0. Proof. Trace of u t u star. This is equal to same thing. U t power half t power half. Since t is positive, there exists a square root. Shruti proved in the class. Okay. Equal to this. And that is equal to, this is just in the form of tt star. So t star t, you can write it. So which is just t power half u star u t power half. Okay. But then u is unitary. Okay. This is equal to identity. Okay. This is just trace of t power of is just t. Okay. So we have got trace of t ut star ut u star equal to trace of t. Okay. So this implies corollary trace of t does not depend on the orthonormal basis. If you have one orthonormal basis, I mean, if you have t, let me write it. If En is an orthonormal basis and Fn is also an orthonormal basis for H, okay, then there exists a U from H to H taking precisely UEN equal to Fn. Okay, that's the definition. Orthonormal basis takes, unitary takes orthonormal basis to orthonormal basis. Okay, UEN equal to Fn. Now this TEN okay, is equal to, I mean, this also implies that U star of Fn equal to En. Okay. Now T U star U Fn that is equal to T U star Fn U star Fn. Okay. That is equal to T En. Okay. So it is because of that ut. Now we know that trace of ut u star is same as trace of t. Okay. So it does not depend on the orthonormal basis, right? You can expand it using En, ut u star. You can fix a basis Fn. If you define the trace using Fn, that is also same as trace defined using En. Okay. Right? So that's what we do. Is it fine? Any question? Anyway, this is something new. You can look at it. Or if you have already gone through, it's all trivial. Okay. Any question? Okay, you can ask me next class also. I end the session.